let's try to solve this question here. So I have a solid cylinder of radius 18 cm. So this is your cylinder and it has a radius of 0.180 meter. This cylinder here is free to rotate about a smooth horizontal axle. So that means you have an axle that fixes this cylinder at this position over here. So the axle will prevent the cylinder from moving to left, right, up, down. It will remain at its position. But because this axle here is smooth, it allows this cylinder to rotate when there's a torque being exerted on it, just like what's happening here. So in this case, the axle allows the object to rotate without changing its position. Okay, so you have a mass of 0.38 kg that hangs from this string over here, and this string is being wound around the cylinder. So you can imagine this mass here is being connected to a string, and the string here is being wound around the cylinder, just like how you wound a string around the yo-yo. Okay, so now they say this system is released from rest. That means probably you have some kind of support initially, but let go of the support, allowing this mass here to fall to fall downwards. Okay, so this mass will take 2 seconds to fall through a height of 5 meters. So you should expect this object here to be moving from a higher altitude towards somewhere lower, and the downward vertical displacement should be 5 meters, and it should take about 2 seconds for this process to happen. Okay, now they ask for the moment of inertia of the cylinder. Okay, let's don't focus too much on what is the question asking for. Let's focus on trying to understand the situation clearly. So if we are talking about a situation involving chapter 8, especially rotational dynamics, it's important that we start by drawing the free body diagram for the objects in the system now. Okay, so what we have in the system now is a cylinder and a mass over here. So you know that this cylinder will be rotating, but it will not be changing position. But since this cylinder is rotating, we cannot just draw a free body diagram just like what we do in chapter 4. If an object we know it can rotate, we should draw an extended free body diagram by taking into account where the forces is acting on. So we cannot just lump all the forces onto a dot. We have to draw the shape of the object first. So our cylinder here will be a circle in shape. So this circle here will be representing the cylinder over here. Next, let's ask ourselves the 5 questions in order to know what are the forces that are acting on this cylinder right now. So you know that this cylinder, does it has mass or not? Yes, it has mass. Therefore, you know that this cylinder here has weight. So weight should be pointing out from the center of gravity of an object. So in this case, the cylinder over here, it's a solid cylinder. So you should expect the center of mass to be at the center of this cylinder. So your weight should be coming out from the center of the cylinder, just like this. Okay, so this is your first question being asked. Yes, indeed, it has weight. Second question is the cylinder here attached to any rope, strings, or cable? Yes, you see that this cylinder here is attached to the rope over here. That means there will be tension exerted on the cylinder at this point over here. So you should draw your tension pointing downwards from the side of the cylinder over here. And this tension, we label it by T. Okay, so this is tension. Next, we move on to the third question. The third question is whether there is any force being explicitly mentioned in the question or being described or labeled in the diagram or not. If you look at the question, they didn't mention anything about you push something or there's a human pulling something, and there's no specific force being labeled over here. So you should expect no external force in this situation over here. Then now we move on to the fourth question, in which we ask whether there's any rough surface or not. Well, one possible place in which frictional force can act on the cylinder is at the axle. If the axle is rough, when you're rotating, you will feel this kind of sound. So that's when the friction is exerted by the axle on the cylinder, causing the rotation to be not smooth. But in this case, we look at our question here. Our question states that the axle is smooth. Therefore, this axle here should not exert any frictional force on the cylinder over here. So you should expect no friction being exerted by the axle on the cylinder. So no friction in this diagram over here. Next, the last question, is the object of interest being attached to any pivot or hinge, or is it in contact with something or not? Well, the cylinder is only in contact with the axle, and the axle actually serves as the axis of rotation of the cylinder. Or you can call this axle here to be the pivot for this cylinder over here, because it fixes the cylinder at this position. The position of the cylinder is fixed at the axle. So in this case, this is a pivot. So you should expect this pivot here to exert a force on the cylinder. Okay, you treat the axle as one object and you treat the cylinder outside as another object. So the axle at the center will exert a force on the cylinder that it is holding. And what is the force that the axle exerts on the cylinder? That will be the reaction force. But what is the direction of the reaction force? We have to determine the direction of reaction force using our logical intuition. So how do we predict it? We take away the axle from the diagram over here. If we take away the axle from the free body diagram, what will happen to the cylinder is the cylinder will be falling downwards. So if the cylinder is falling downwards, that means the axle is there to prevent the cylinder from falling downwards. The axle is there to prevent the cylinder from falling downwards. That means the axle must exert a force that is in the opposite direction, which is pointing upwards. So the axle exerts a force pointing outwards to prevent the cylinder from falling downwards. Therefore, you should expect a reaction force pointing upwards. And this reaction force is exerted by the axle on the cylinder. Okay, so this is a situation. We have asked ourselves 5 questions. So this is the free body diagram for our cylinder. But of course, it is incomplete until we label the distance over here. So this distance over here is 0.180 meter. Okay, now I would like to talk about a hypothetical situation, what I mean is not this situation, just a hypothetical situation. So let's say today you have a tension which is pulling in this direction also. Let's say I'll call this star because it's hypothetical, just a what if situation. So what if you have a tension pointing in this direction, then where should your reaction force be pointing towards? In that case, let's think, if we take away the axle from the diagram, then the cylinder will be falling like what we predict earlier, right? But now, if we still have this tension, let's say we have a rope pulling towards the left, then what will happen is the cylinder will be falling while moving to the left. It will be falling while being moved to the left because of the tension being exerted to the left. Therefore, the axle is over here to prevent the downward motion and the leftward motion. So if the axle wants to prevent a downward and leftward motion, the axle has to exert a force which is upward and rightward in order to prevent that motion from happening. So if today you have this tension over here, then what will happen is your reaction force will be pointing in this direction. Because if you point in this direction, you will have a component which is Rx that can balance out the tension that you have over here. So the tension is to the left, so your R, you have a component that is pointing to the right, and they should balance each other. Only when they are balanced each other, the cylinder will not be moving to the left or to the right. It will remain at its position. So at the same time, we have weight and tension pointing downwards. So therefore, our reaction force must be pointing upwards in order to balance the weight and the tension. Or else, if your reaction force is pointing, let's say, in this direction, then there will be no force pointing upwards really. Then the net force will not be zero because the whole forces will not be in equilibrium. Then the object will be falling already. The R has a component pointing upwards because it needs to balance the weight and the tension. The R has a component in the X direction pointing to the right because it needs to balance the tension that is pointing to the left. So the direction of the reaction force depends on what are the forces that are acting on the cylinder as well. Okay, so reaction force is not always pointing upwards. It depends on the situation. Okay, so I'm here just showing you a what if situation. What if you have a tension pointing to the left? Then your reaction force should be pointing in this direction so that you can have a component that is pointing in the right to cancel off the tension pointing to the left. Okay, just an extra info. Okay, so this is the free body diagram for the cylinder. Let's move on to the free body diagram for this block over here. So the block, we can represent it with a dot. Because this block over here is not rotating, we don't need to draw an extended free body diagram. Just a simple free body diagram will do. Because the block here is not rotating. If it's rotating, then we might need to consider the whole box, the whole shape of the object. But now it's just going up or down, so we don't need to draw an extended free body diagram. Okay, so for this free body diagram, we draw it a bit faster. You have weight, but since you have two weight over here already, you should call one of it as weight of the cylinder, then another one is weight of the mass. Then at the same time, you know that this mass over here is connected to a string, so there should be tension as well. And since this tension and this tension are both belonging to the same portion of the rope, the same section of the rope, that means this tension and this tension here should have the same magnitude. Okay, if they are from the same portion of the rope, you should expect a same tension. But if the same rope, let's say this same rope over here, go through, let's say in this direction, then if this tension here is called T1, this tension here is called T2, T1 and T2 not necessary to be equal, because this is one portion of the rope, this is another portion of the rope. Once it goes through a pulley, you can consider them as two different sections already. So the tension not a must to be the same. So this is an important characteristics when you are considering pulley in chapter 8. Okay. So this is the free body diagram. We have completed the free body diagram for the mass. You can ask yourself the other three questions and you find out that there's no external force, there's no normal force, and there's no friction for this free body diagram. So we are done with our free body diagram. Let's label them clearly. This is the free body diagram for the cylinder. This is the free body diagram for mass Vm. Okay, so once we have drawn our free body diagram already, we can actually analyze this two free body diagram using sum of torque and sum of force. We know that this object here is not moving, so it is rotating. Okay, why do you know it's rotating? Because when you release this block here, letting it fall downwards, you know that this object here will start to accelerate downwards. Okay, this mass here will start to accelerate downwards, so you should expect an acceleration over here. Okay, and because this acceleration is pulling on the string over here, you should expect that this cylinder will start to rotate as well. So it will start to rotate clockwise because you're pulling in this direction. So you should expect an angular acceleration in this direction as well. And this acceleration and this angular acceleration should be related using A equals to R omega. Because you assume this string here never get loose. So if this one accelerates by how much, then any point on the radius of any point on the circumference of the cylinder will move by the same amount as well. So if the block accelerates with acceleration of A, any point on the circumference of the cylinder will also be accelerated by A. So the angular acceleration is alpha, so you can relate the A and the alpha this way. A is equals to R alpha. Okay, so this is just to understand the situation more clearly and to know how to relate between one free body diagram and another free body diagram. Okay, so let's start and analyze the cylinder using sum of torque equals to I alpha. So if we are analyzing sum of torque equals to I alpha, we have to define the direction. What is the positive direction? Okay, if you remember when we do sum of fx equals to ma, right? We take the direction of the acceleration as the positive direction, right? So here we will take the direction of the angular acceleration as our positive direction. We will do the similar thing. So we will take direction of angular acceleration, which is clockwise. we'll take this direction of angular acceleration, which is now clockwise, as the positive direction. Okay, so what does it mean is if your torque is pointing anti-clockwise, then it's a negative direction torque. If your torque is clockwise, then it's a positive direction torque. Okay, so now we define clockwise as positive because we want to follow the direction of the angular acceleration. So if we do that, then our sum of torque will be equals to I alpha. Then our sum of torque over here, we look at this free body diagram here. What are the torque that makes up our sum of torque? We know that the reaction force and the weight of the cylinder will not cause any torque to the system because the reaction force and the weight are both exerted on the center of mass, on the axis of rotation. So for these two forces over here, the R, the distance from the axis of rotation to the position of the force, will be equal to 0. So the R for both forces over here will be equal to 0. So your RF perpendicular will be equal to 0 because R is 0 for reaction force and weight of the cylinder. So the only force that causes torque will be the torque produced by the tension over here. So now we can say the torque produced by tension will be equals to I alpha. Okay, but we have to check the direction of the torque, of course. The direction of the torque is the tension is pointing this way. So if you pull the cylinder like this, you should expect the object to rotate clockwise, right? If you pull, it will rotate clockwise. So clockwise is positive direction. So this torque in front, we can put a positive sign. If the tension is pulling on the left-hand side instead, then the object will rotate anti-clockwise. If the object is rotating anti-clockwise, then that is negative direction. Then we need to put a negative in front of the torque produced by tension. But in this case, the tension is on the right hand side, so if you pull like this, you rotate clockwise. So we decide clockwise is positive, so we put positive, torque produced by tension equals to I alpha. Okay, so the torque produced by tension we can determine it using R times, let's look at what is perpendicular to our R. Our R is pointing from the center of mass over here to the position of force. So this is our vector R over here. So what is the component of tension that is perpendicular to R? Well, the whole tension here is perpendicular to R. There's no parallel component of tension to R. The whole tension here is perpendicular to R, so you can just substitute tension over here. Okay, I should write in black pen. So this whole thing here is just tension. You don't need to resolve to any components for here. And now this is I, and alpha we know can be related to A divided by R. Okay, over here you can write A divided by R will be equals to alpha. Okay, so once we reach here already, right, we know that if we do our substitution, we will have 0.180, but we don't have tension. And we don't have tension, so we cannot find our moment of inertia straight away. And we also don't have the acceleration as well. So we cannot find our moment of inertia straight away. But we know that acceleration and tension here, they are just things that we learned in chapter 4. So the tension here, probably we can find the tension from this next free body diagram here. Because this next free body diagram here also involves tension. And we know that it will involve sum of F equals ma because this object here is also falling with an acceleration. So let's move on to the next free body diagram. For the next free body diagram, we will take the direction of acceleration as the positive direction as well. So for this case, we will take direction of acceleration. This one is linear acceleration here. We will take direction of acceleration, which is now downward, as the positive direction. Okay, it's important to write this sentence to allow us to know where are you defining to be positive. Or else sometimes we don't know where are you defining as positive, right? We might be confused with your sign. But if you write clearly, it should be fine. So here you do sum of Fy equals to may, because you know this object here is not at rest, and it's not remaining at rest, and it's not moving at constant velocity. You know it will be falling down with an acceleration. So you use sum of Fy equals to MAy. So for this situation, we will take what's pointing in the direction of acceleration, which is weight of the big mass M. Then you minus what's pointing in the opposite direction of acceleration, because opposite direction of acceleration is negative direction. So we put negative tension, and this will be equals to MA. Okay, the whole acceleration is pointing downwards, so you can just replace AY with A. Okay, because there's no AX. The whole acceleration is pointing downwards, so the whole magnitude of acceleration is just the Y component of acceleration. Okay, so when you reach this step already, I believe you can do a bit of substitution. You know the weight here is 0.38 times 9.81. But again, you don't know the tension. But I know that this is 0.38, and this is acceleration is A. You don't know A. Okay, but even though you don't know A, okay, you don't know T, you don't know A, it seems like there's still a lot of unknown that you don't know. But actually, A can be determined. How do you determine A? Well, they tell you that the mass takes 2 seconds to fall a height of 5 cm. So if it tells you the downward displacement is how much, and it tells you the time as well, actually you can determine the acceleration through kinematics of linear motion. To be more specific, you use the kinematic equations. So let me write down the SUVAT for now first. Okay, so for SUVAT, we just keep it standard. For SUVAT, we take up as positive, down as negative, because we have been doing it like this for chapter 2, right? We keep it like this. So if this is the case, then our SY, UY, VY, AY, and T, we will fill the blank first. We know SY here is the vertical displacement, and the vertical displacement is pointing downwards, therefore it's negative 5.00 meter. How about the U? The initial velocity in the Y component, initially the object is at rest, then only it released from rest, right? So in this case, the Y component of initial velocity is 0. How about the final? You don't know, because they didn't tell you about it. What's the acceleration? That's what you want to find to put in over here. And what's the tension? Tension. What's the time? What's the time duration for this journey over here? Well, it's just 2 seconds. So let's write in 2 seconds. So we are interested to find the acceleration, and we are given information about the displacement, the initial velocity, and the time interval. So to determine the acceleration, the suitable equation will be Sy equals to Uyt plus half Ayt squared. So if you perform our substitution, it will be negative 5.00. Then it will be 0 plus half Ayt squared. T is 2.0 squared. And if you move through your calculation, use your calculator, I believe you should get Ay to be negative 2.5 meter per second squared. So if Ay is negative, then we know that negative means it's downward. That's why if you write it as a vector, right, the acceleration here will be 2.5 meter per second squared, and it should be pointing downward. Okay, so what am I doing here is I'm re-expressing it in terms of vector. I write the magnitude of the vector, then the direction of the vector. Now I know that the direction of the acceleration is pointing downwards. So if I bring it back to this block of calculation over here, I know that my acceleration is downward. So downward I assume as positive. So I will sub in the positive value for 2.5 inside here. Okay, because I define downward as positive for this block of calculation, and I happen to know that my acceleration is pointing downward. So if I substitute it inside A over here, our A over here should be a positive value, not a negative value. Okay, so what should I substitute here? Let me erase the A and replace it. I replace it with 2.5. And now if we replace it with 2.5, I believe we can obtain our tension to be 2.78 Newton. Okay, and once we obtain our tension, we can sub in our tension over here, and we can sub in our acceleration over here. Remember our alpha over here, we define alpha as the positive direction. So this alpha here must be a positive value. And if alpha is positive value, r is also positive value, the acceleration must also be positive value. So A here will be taking this 2.5 positive value. Okay, so if you substitute in everything, I believe you should get your moment of inertia to be 3.60 times 10 to the power of negative 2 kg meter square. And this is how you can solve this question over here. Again, the question seems a bit complicated, but the steps are quite standardized. You start with free body diagram here. Then if you see the object is rotating with an angular acceleration, you analyze it using sum of torque equals I alpha. But before you analyze it, make sure you define the direction clearly, where you take as the positive direction. Usually we take a direction of the angular acceleration as the positive direction. So our alpha here should always be a positive value if we take the direction of alpha as the positive direction. Okay, so you can proceed through a calculation until you are stuck. Then you move on to the next free body diagram. In this free body diagram, it's undergoing acceleration. So we analyze it using forces instead of torque. It's not rotating, it's just moving downwards with an acceleration. So we analyze the free body diagram and we use sum of Fy equals to MAy. But now we define downward as the positive direction so that we can substitute a positive value of acceleration. Because we know the acceleration is pointing downward, and we define downward as positive. So we sub in a positive value for acceleration over here. Then we take what's pointing in the direction of acceleration minus what's pointing opposite the direction of acceleration. So this is what we have done in chapter 4. So we know that we are stuck here because we don't know the acceleration. So we look at the situation here. The situation here allows us to obtain acceleration through kinematics of linear motion. So we do our Suvet equation. We use this Suvet equation here to obtain the acceleration. But even though this acceleration here is negative, we know that this acceleration negative here just means that this acceleration is pointing downwards. So if you write it as magnitude and direction downward. Therefore, when you use the acceleration, you know that you should not put negative sign here because you assume downward here as positive direction already. So you put in positive 2.5 over here. Okay, another way you can do it is you can change down as positive, up as negative. So it will be a little bit different from what you do in chapter 2. So you get a positive answer here, then you can straight away substitute. Again, if you write this first sentence here, then we can understand what you're doing. The most important thing is you need to tell us where you define as a positive direction. So here we define downward as positive. So if our acceleration is indeed pointing downward, so we will sub in positive. If this acceleration is upward, and now we define acceleration downward as positive, but this acceleration here is upward, then we substitute negative 2.5. But now this is downward, so positive, positive. Okay, then from there we get our tension, then bring back our tension into the first block of question, then we substitute everything, we get our moment of inertia. So this 3.60 times 10 to the power of negative 2 kg meter square is the moment of inertia of the cylinder over here.